In this tutorial, I want to talk about transistors and how to use them to interface to your microcontroller. Generally, they'll be used when you have a load or something you want to interface to that has it draws too much current or has too high a voltage for the Arduino or the microcontroller to drive. And transistors come in many different sizes and packages, and the bigger ones tend to dissipate more power, so they're used in heavier applications. This is probably the size that you'll be most most likely be using for interfacing to a microcontroller. And maybe something bigger like this. I don't know how much power you might want to be driving. And transistors also come in two different general kinds, what they call BJTs, which stands for bipolar junction transistors, which is the more common one that you'd likely be using. And the other one's called an FET, field effect transistor. And actually there's probably lots more of those around in the form of what's called MOSFET, which stands for metal oxide semiconductor field effect transistor. And inside your microcontrollers, and in fact any chip that has lots of transistors in it, they're all MOSFETs. And so there could be tens of MOSFETs in a chip to literally millions. I believe the CPUs in your PC have, I believe I heard a figure of something close to 1 billion transistors on the chip. And they're all MOSFETs. So I'm going to talk mostly about the BJTs, and they come in two forms, a PNP and an NPN. And I'm going to draw the schematic symbol for each type. So the schematic symbol for an NPN looks like this. And I'll give you the names of the leads in a minute. It has the arrow here. And the three leads, and you probably noticed in the examples I had sitting there, they all had 3 leads. And the 3 leads are labeled C for collector, B for the base, and E for the emitter. And essentially what a transistor can do is you can control the amount of current flowing through this way in the same direction as the arrow by controlling the amount of current flowing into the base. The more current in the base, the more current that flows and the more current that flows in the collector to the emitter. And there's an amplification here as well. It doesn't take very much base current to control a large amount of collector current. So this is an NPN transistor. These are more common, but the opposite polarity to this is called a PNP transistor, and I'll draw it in the same form. Collector here. This is the emitter, except the difference with this schematic symbol is the arrow points the other way. But the leads are still called the same: collector, base, and emitter. But in this case, the current can only flow this direction. And when you want the to control the current flowing through this, you draw current out of the base. In the case of the NPN, you inject current into the base. A simple rule of thumb for remembering what the polarity of the bipolar transistor is by looking at the arrow. So this arrow here, you could say it never points near, and that's an NPN. The PNP is the other one. It does point near. So they're used in different applications to do the same thing. Now, I'm going to talk about probably one of the most common transistors that people use, and it has the number 2N3904, and that is a PNP transistor. It's of this form. It's what they call a complementary. It's very similar in characteristics to the NPN, but it's the different polarity, and its number is 2N3906. And like I said, these transistors are very common. You can buy them very cheaply if you want to buy a bunch at a time. You might get 100 of them for 10 or 15 cents each. Not a lot of money. And they come generally in this package here with the 3 leads. If you were to look at it from the end on, I'm not sure how this is showing up, but you can see how it's kind of a half round shape. And then you've got the flat surface here, the flat face. And written on that face, whether it'll show up in the camera here when it focuses there, can't tell, I don't think it's focused. Anyways, the number is written on there. And in the case of this one, it actually, they've also written on here what the leads are. But typically it's done, the leads are laid out this way. So there's the flat face of the transistor, the back side. And then you got your 3 leads here. And generally it's base, collector, emitter. And it's the same for both the NPN and the PNP. In a package like this, I believe this one is the same, base, collector, emitter. In a package like this one here, the collector is the case. That's one of the connections. And then on this one it's actually marked. You got the emitter and the base. And the reason why in this case the collector is the case is because the chip that the transistor is made out of is bonded to this case, and that's where the heat's generated. And the reason why it's in such a big case like this, for one thing, the chip is quite large. It would be, maybe a quarter of the size of my fingernail there. If you cut my fingernail into quarters, the chip in there would be something that sized. And it's mounted in a package like this so you can stick it against something that's called a heatsink, which is a large chunk of aluminum usually that has fins on the side, and it allows the heat to be dissipated quickly into the air. And sometimes fans will be used to blow the heat off the heatsink. This is a power transistor. It can handle a couple hundred volts, and it can handle I think 15 amps. But the transistor that you're most concerned with would be one of these two probably, and they can handle about 40 volts between the collector and the emitter maximum, and a maximum of about 200 milliamps flowing through the collector to the emitter. Now, transistors can be used as switches, which is primarily what I'm going to talk about here. In fact, it's all I'm going to talk about. I'm not going to talk about them used as linear devices. But there's also a linear relationship between the amount of base current and the amount of collector current flowing in there. So you can use a transistor as an amplifier, using a small amount of current to control a large amount of current. And that way you've got current flowing through the transistor, and there's a voltage developed across the transistor as well. It gets hot. But in our case, we're going to inject enough current through the base here to turn the transistor on, what they call turn it on hard. And that way there's very little voltage drop across this collector emitter junction, in the order of 200 to 300 millivolts when it's turned on. You have to give it enough base current to do that though. So let's look at a few other things here. So to connect the transistor up to your microcontroller to a load, this is how you do it. This is the microcontroller. This is the I/O pin. Now you need to have a current limiting resistor in the base lead. This goes to the base of the transistor. The emitter is here, and we'll put the emitter to ground. And then the collector comes out here, and we'll put in some kind of a load. I'm just going to draw it as a box. It could be a motor, it could be a resistor, it could be an LED and resistor combination, but that's the load. And we will tie this to some voltage. Now it doesn't have to be the 5 volts that the microcontroller is tied to. It could be a higher voltage. it could be 12 volts. This is the advantage of using this transistor, is that you can supply a load with more current than what you can get out of the microcontroller, and also provide a load with more voltage than you can get out of a microcontroller. So to turn this circuit on, in order to get current to flow through here, you raise this pin on the microcontroller to 5 volts. You make it go high. And so current will flow through the resistor, into the base, and through into the emitter. And then if it's enough current, then the current will flow through the collector to the emitter as well. Now, how much base current do you need to get collector current flowing? Well, you need to know how much current will be in the load here. You should know that because you also want to size your transistor so that it can handle the current that this load needs. And as I said, the 3904 can handle 200 milliamps, but that's a maximum. If you ran it at 200 milliamps, you would have a good chance of burning this transistor out fairly quickly. So I would run it somewhere around 100 at the most, or less. Now, there is a parameter related to the transistor, and if you want to search the internet for these devices, you can find a spec sheet for the transistor, and it will tell you the absolute maximum ratings, the maximum voltage this could withstand. So for example, when you've turned the transistor off, there's no current flowing, so this lead here will be pulled up to the same voltage as the power supply voltage. And so you'll have 0 volts down here and whatever the power supply voltage is across on the collector, and you'll have a voltage across the collector. And there's a collector emitter. And there's a limit as to how much this transistor can withstand. In the case of a 3904 and a 3906, that's 40 volts. So V up here has to be less than 40 volts. Keep that in mind. This load here, the current for the load IL has to be less than 200 milliamps for a 3904, 2N 3904. So these are some of the considerations that you have to make when you're choosing how you're going to drive your load. If your load has much more current or voltage than that, then you're going to have to find a different transistor that can handle that. Now, to turn that transistor on, and we want it to turn on hard, we call that saturation, and that's the state that we're most interested in. When the transistor is turned on hard, there is very little voltage between the collector and the emitter. And so there isn't much heat generated by the current flowing through here. And the transistor won't get hot. Same as when this is turned off, there's no current flowing through here, even though there might be up to 40 volts across the collector and the emitter. But no current flowing, no heat dissipated. So, how much current do we have to inject into the base in order to get this transistor to turn on hard, to saturate? So you look at your load current, and whatever value it may be, say we're looking at, I don't know, let's not do numbers just yet. Let's look at something. If you get a spec sheet for the transistor, somewhere in the sheet will be a parameter that is written as H sub F sub E. And what that is, it's also sometimes called beta, although beta I think is a term that's going by the wayside. HFE is the correct parameter, and it relates to what's called the current gain of the transistor. And it's simply the ratio of the collector current over the base current required to get that collector current. And under most circumstances that you're going to use this transistor for, its minimum value will be about 100. So it means for every milliamp of base current you inject into the base, you could control 100 milliamps of current through the base, or the collector and the emitter, and the transistor will be fully switched on. So that's a good number to know. And I tend to use a little smaller number than that because I want to guarantee that the transistor is saturated under my circumstances. So will use a smaller number so that my base current will be a bit higher. If you inject more base current in there that's required to get the collector current to flow, it doesn't matter. It's not going to hurt the transistor. Although there is a parameter, another absolute maximum parameter is the maximum amount of current you can inject into the base. But it's actually quite high. It's similar to this 200 milliamps. So you're not likely, especially with a microcontroller, not likely to inject too much current into the base to cause damage to the transistor. So if my collector current was 100 milliamps, for example, my base current would be 100 divided by 100, so it would be 1 milliamp of base current. So now I am able to control a large amount of current, 100 milliamps, with very little current from the microcontroller. In a previous tutorial, we looked at the voltages produced on the pin of a microcontroller, how it varied, how it dropped with more current that you drew through the either sunk into the pin or sourced out of the pin. And you want to keep that current low so you get the full voltage range on the I/O pin. So we want to limit that. Now the reason why there's a current limiting resistor in here is because when this transistor is running, the maximum voltage you're going to get across this base emitter junction is about 0.7 volts. For that, there's a diode in here, but I think I'll do another tutorial separately on diodes, and that'll explain this 0.7 volts. But that's just the characteristic of this transistor when it's properly running. And so to figure out this resistor here, you have to do the calculations first of all to figure out the base current, and then you can model the this connection here kind of like this. You've got the resistor, and then you've got this diode, which is not a light emitting diode. In my tutorial on light emitting diodes, I talked about the drop across it. It was be about 1.5 to 2 volts. And this diode here, it's only 0.7. And then it goes to ground here, and we've got 5 volts up there. And in this example, we've got an I which is equal to 1 milliamp. And remember, the current flows through the resistor and this base emitter junction diode. So to figure out the resistor that we need to limit the amount of current there, we just simply rewrite Ohm's law, and we go R equals the voltage across that resistor divided by the current flowing through it. And the voltage across it is 5 volts minus the voltage drop across the diode here, which is 0.7. So we've got 5 minus 0.7 divided by, in my case here, 1 milliamp. And that's how you come up with the value of the resistor. If this voltage here, say you're using this for a different application, and you might have a higher voltage here to turn on the transistor, you could almost ignore this 0.7 volts drop. Say you're using 12 volts to turn on this transistor, you can almost ignore it, and your calculations will be close enough. But when you're getting down to the microcontroller voltages, 5 volts or even 3.3 volts, which some of the Arduinos use, are 3.3 volts, it's a significant number relative to the 0.7 volt drop across the base emitter junction. So you need to include that in the calculations. So just remember that when you're doing this. So when you do the calculations here, you get 4.3 k ohms. And I talked in the resistor divider tutorial about the preferred values, and the closest value to 4.3k, I would go lower because you want to make sure there's more than enough current here, so I would choose a 3.9 k ohm resistor. 4.7 is the next one above. So that is about all we need to talk about here. When this load is purely resistive, like an LED and a resistor, you can use the circuit just like this. If you're switching an inductive load, such as a motor, you need to put a diode across the base or the emitter collector because the inductance in the coil stores a bit of energy, and when you switch it off you get a very sharp voltage spike, and that can damage the transistor. I think I will address that in another tutorial. This is very specific. But if we were just running an LED and a resistor combination here, this is all you need. Now I just talked about using an NPN transistor down here, and we call this low side switching. Sometimes your circuit demands that the load is down here at ground, and so we need to use a PNP transistor to do the same kind of thing, to switch it. Now there's limitations when we use a PNP transistor, but I'll talk about that. So to put a PNP transistor in, we have to orient it the right way, because as I said before, the current flows only in one direction in the transistor, depending what it is. And I know the BJT designation for this type of transistor, bipolar junction transistor, it does not mean that the device is bipolar. It does not mean that the current will flow in the other direction in the device. It won't. So in order to use a transistor where you want to switch on the upper side, the high voltage side, here's our microcontroller again. We have our, again, we need another current limiting resistor and the transistor. Now I have to turn the transistor over from where it's drawn in this picture. I have to put the emitter up at the top because that's the way the current flows. So the emitter goes here. This is your voltage, and I got to talk about the voltage in a minute here. And then our load could be a light bulb, it could be LED resistor combination. It goes to ground there. And in this case, the base current flows in this direction. In the previous case, you got the collector current flowing this way, and the base current is flowing this way. I'll draw it out here, IB. In this case, the load current, IL, is flowing this way, and the base current is flowing the other direction. It's going out of the base, IB. So to turn this combination on, we need to bring this pin to ground so that we get current flowing through the resistor. To turn it off, we have to bring it up to the same potential as this one, because remember, we've got a bit of a base emitter voltage drop. It's the same thing here, except it's 0.7 volts again, but it's the other polarity. This is plus, and that's the minus side of 0.7. And so in this case, I'm not going to be able to switch something that's at 12 volts here, because when I put this to 5 volts, we still have a voltage drop across this resistor, and you'll still get current flowing through here, and the transistor will be turned on. So this is the only caveat that we have with using a PNP transistor and switching this load. The voltage that you're driving this load from has to be the same as the switched voltage on the microcontroller. I can show you using a couple of transistors another circuit that allows you to switch with 5 volts and switch a much higher voltage. We'll get into that in a minute here. Now, the calculations for the base resistor, it's the same as the previous one. The collector current flows this way through the load, the base current flows this way. This transistor has an HFE as well. Now, when you look through the data sheets for a 2N3906, which is what this one here is, you may find that the HFE for a PNP transistor is lower. And the reason for that is, as the manufacturing process is different between a PNP and an NPN, and the transistor is not as efficient. I can go into the details of the construction of a transistor and the mobility of the charge carriers, etc., and what they call the majority carriers. In an NPN device, the majority carrier is called are electrons, and the majority carrier in a PNP device are called holes, or lack of electrons. The electrons are more mobile than the holes, and therefore the transistor conducts better. But these are very similar anyways, and you'll find the HFE is very close to what it is for a 3904. But you do the same calculations. You figure out the base current from IB equals I, collector or load, divided by HFE. And do the same calculations again to find the base resistor here. So this is a way of switching with the opposite polarity a load that's close to ground. If I want to switch a load with a PNP transistor with a higher voltage, I need to use two transistors, and I got to the two transistors will do something that we call level shifting. So, whoops, I'm running out of blank paper here. I'll just draw it underneath. So we will keep our PNP where it is in the circuit, and our load is down here. We need a base current limiting resistor in the PNP base. Now we can hook up another transistor down here. This time it's an NPN and it goes to ground. Another base limiting resistor, and that one goes to the microcontroller. And we need another resistor here just to make sure that this transistor turns off. So what happens here, I'll draw it in a second here. So to turn off this transistor, I have to turn off this transistor and pull this lead to the power supply. So we'll put another resistor in here. I'll put it in now. Same potential, this could be 12 volts or whatever. So to turn off this transistor, I turn off this one here. So there's no current flowing through here, no voltage drop across that. It pulls this pin up here and it turns off the base current. To turn on this stuff, I need to turn on this transistor, which draws this point down to ground and draws current through the base and emitter of the transistor. So it kind of inverts the signal as well. To turn on this load, I have to raise this high. Actually, it works. Well, it's not this. Yeah, it's the same. Sorry. It is the same polarity. Got it wrong there as the other circuit. But anyways, this is how you interface it using two transistors. Now, obviously, the current flowing in the collector here for this transistor is going to be much less than in my previous example. It'll be whatever the current flowing through this resistor is plus the base current here. You calculate the base resistor the same way as you did up here, except your V now is higher voltage. So it's V minus the 0.7 volts here. And so your resistor is probably going to get a bit bigger than if this was a 5 volt. So if this was 12 volt supply, you'd have a certain value of resistor based on your base current. If this was a 5 volt supply, your base resistor will be much lower. So the value of the base resistor here, if the supply was 12 volts, would be a certain value. And if this was 5 volts, the resistor here would be actually smaller because you have less voltage drop across it in order to get that current flowing through. And this resistor here, you got to make it small enough that it's going to be smaller than this one here. But not so big that you have too much current flowing in this transistor here. So let's throw some values in here. This is R2, this will be R1. We'll make V equals 12 volts. So we want to figure out what R2 is here. This is 100 milliamps. And our HFE for the PNP is, we'll call it 60 in this case. So our IB for this transistor here, this is IB, will be 100 milliamps over 60 and equals, I'll just punch that in my calculator, can't do it in my head, 60, and it will be 1.7 milliamps. The voltage on that resistor will be 12 minus 0.7 volts, which is 11.3. So R, we'll just do it here, 2 is equal to 12 minus 0.7 divided by 1.7 milliamps. So 1.7 milliamps divide gives me 6.6K. So a preferred value for that would be 6.8 would be the closest. So we'll use 6.8K here. Can't remember what the next lowest value is. 5.6, I believe. So R2 then is 6.8K. So and this one is connected to the 12 volts as well. And so I don't want a huge amount of current flowing in here. It's kind of a waste of current, but I want to make sure that this resistor is big enough to swamp this one here. So, or small enough, I should say, to draw the current out of there. So I could make this say 2.2K, just for figure here. And that would be enough to turn this transistor off when you connect, when you've turned this transistor off. And then the collector current flowing through here is 2.2K, so it's 12 volts, and I'm going to ignore the drop across here, which is about 0.2 volts, but I equals V over R, so 12 volts divided by 2.2K is, we got 5.5 milliamps flowing through here. So to figure out this resistor here, we got an HFE of 100 on this one, so 5.5 divided by 100 gives me 55 microamps, and so R1 will be 5 volts minus 0.7 gives you 4.3 volts over 55 microamps. 4.3 divide, so that gives me 79K. So you can see how the value of a resistor is getting bigger in here, because you don't need as much base current to drive this transistor on. Anyways, that I believe is a good quick tutorial on using transistors. The things to remember are the bigger, physically bigger the transistor is, generally the more current it can handle, the more power it can handle. I would expect the kind of loads that you're playing with shouldn't be more than maybe a couple of amps at the most. The most common transistor you're likely to use is a 3904 or maybe a 3906, depending on your application. Points to remember is that the base current is always less than the collector current, and it's by this ratio called HFE, and you need to look that up. But I think the numbers I gave you for these two different transistors, 60 for this 3906 for the PNP and 100 for the NPN, should be good. Remember that both transistors will have a voltage drop across the base emitter junction. In an NPN, the polarity is of course this way, plus on the base and minus on the emitter. I go over to the PNP, it's the other way around, it's plus on the emitter and minus on the base, but it's still the same voltage. You got to take that into account when you're calculating your resistors here in the base current limiting resistors, if it's for the microcontroller voltages. 12 volts, you can almost ignore it. It doesn't make that much difference, especially when we're picking our preferred values. So even if I just ignore that 0.7, I'll just redo the calculation here. It's kind of curious. 12 divided by 1.7 milliamps gives me 59K, or 5.9K. So if I chose enough, the next value down 5.6K, it's pretty close. It'd be all right. Even 6.8K would probably be giving you enough base current to get this transistor to turn on. The spec sheets spec these HFE values, but they always tell you that that's the minimum that they would expect to see in a device. Switching an inductive load like a motor or a relay requires some protection here, and I think I'll talk about that in a different tutorial. I've gone on long enough in this one. So I hope that you got something out of this tutorial. I ran by it pretty fast, but the beauty of a video is you can always rewind it and start it again and have a look. I hope this tutorial was useful. Hope you enjoyed it. Thanks for watching. See you next time.